Hi, welcome to the Calculus 2 lecture series. We are in the unit number 2, Techniques of Integration. We start our lecture number 11, Approximate Integration. For the lecture number 10, the previous lecture, we talked about the strategy for taking the integration. And sometimes the integration, like I mentioned in the video, sometimes the integration, you just cannot get it. You cannot use the algebra way to find the integration. So one way we can do it is try to use the numerical method, try to approximate it. Okay, so that's what is this lecture we're going to focus. So let's take a look at our lecture notes here. Okay, so the key concept is here. Okay, so let's take a look. The key concepts here, we just want to approximate the definite integral. And by using the left endpoint, right endpoint, and midpoint, and trapezoid, rule, and the Simpson's rule. Okay, and then the next things we're going to talk about, after we do the estimations here, then we want to be able to estimate the maximum error for your approximation. Okay, so the sum of so for example, like we talk about the left endpoint, right endpoint, middle point, we kind of use this method when we first try to use Riemann sum concept to derive the definite integrals, right? So here is the same thing, when we try to estimate the approximate the definite integrations, and we won't be able to numerical carry out, we still can use the left hand point, the right hand point, and the middle point. And in here, we're going to introduce two new methods here. We'll call it the trapezoid and the Simpson. Of course, after we estimate, and I want to be able to find out if I use this estimation, if I divide my interval into this many sub-intervals, what type of the maximum error, how much I'm going to away from the true integration values here. Okay, so like I mentioned, we're kind of familiar with left endpoint, right endpoint. So let's just take a look. So like if this is so what is left end? Okay, so let's assume this is my functions, right? So this is my f of x functions. And then in here, I have this is A, and this is B. So here, I am looking for, right? So I'm looking for the integration of A to B, the f of x dx. And I won't be able to make algebraically to derive it, so I can say I can use the left endpoints here. So what is the left endpoints? That means I divide my intervals here to many sub-intervals, right? So this is x1, x2, x3, to this is xn minus 1, right? So here, then what is the left endpoint? That means I'm using the left end of your rectangle. So here, this is my left end. Let me use a different color better here. Okay, so this is my left end. So from the left end, you find a rectangle. So this is your left end, you find a rectangle. Then here, this is the left end, you find a rectangle. So as we know, this is what we learned, when we first introduced the Riemann sum concept. So this is the same thing. So I use the left end. So I know this one can be approximate by we use this notation L to the n, right? That's left end. So will be, so for each one's here, each subinterval, the length will be the delta x, right? So of course, the delta x will be b minus a divided by n. So the area can be approximately by those pink rectangles, right? So it will be the delta x here times, so it's the width times the height. So the height here, the first one is what is f of a plus the second one is f of x1. Then da to the last ones will be what? Will be f of what? xn minus 1, correct? So this will be, we call this a Lefthand approximation. And we, like I talked before, in the Riemann sum, we use this concept. So it's a pretty easy concept to, to understand. It's also, it's kind of like a review. Okay, so now here, this is my, did I do the same graph here? It's always very difficult to get the same thing. All right, so here. Okay, so if this is my f of x again, right? So this will be, a, and this will be b's, right? Now, the same way I divided my interval into many, many intervals here. This is n minus 1. This is x1, x2, x3, right? Then for each one, you will have rectangles here. That is here, right? Okay, so now if I want to use the right-hand point, right hand, that means in here. So this is my first right hand. So this will be my first rectangle. Then here will be my what? My second rectangle. Then here, this will be my third one. And the so the last ones here will be what? Will be this ones, right? Okay, so the same way for the right hands, so I'm still, okay, approximately to my integration AB f of x dx will be what? The same things here, delta x will be b minus a divided by n, right? So what is here? So I will use the right n. So I use the notation of Rn, right? So still the same, I use the width times the height or the length. So what is the first length is right hand. So the first one here is what? Will be x1, right? Now you have x2 and to what is the last one? Last one you use b's, right? So it's f of the b's here. So this is what we call this the right hand rules here. Okay, so let's take a look at the midpoint. So midpoint, we also did this when we try to derive by using the Riemann sum concept. We also talk about the here. Oh, here. So let's take a look at the, okay, so this one's here, right? So this is my f of x. So the same way I have, this is my A, this is my B, and I divide into several here. So this is x1, x2, x3 to the xn minus 1. So what is the midpoint rule? So the midpoint rules will just be, so let me color that for you. So that means that the middle point of A and the x1 here, right? So that means I'm this is the midpoint. So touch the curves here. So I use this to draw the rectangle. So here is the same way, the midpoint is here, right? So touch the curves here. So I use this rectangle to estimate. So the same way here, if you find the midpoint, here, then this will be the rectangle I'm using. And the same way is here, right? So if you find the midpoint here, then this will be the last rectangle. So each subinterval has a midpoint, right? And so we know that each midpoint. So how do I find the midpoints here? Will just be what? Will just be the xi minus 1 plus xi divided by 2, right? So I can say this is the average. So I use x bar I to represent it, right? So this will be the x1 plus a divided by 2, x2 plus x1 divided by 2, x3 plus x2 divided by 2, right? So this is what we call this what? This is the this is x bar 1. So let me see here. Let's use a color. So this will be, so here, this will be x bar 1. And here, this will be x bar 2. This will be x bar 3, right? And this will be x bar n's here. So now I still, so I should say so approximate. So I can still say the AB, this is going to be f of x dx is going to approximate by the middle point n. So what is the middle point n here? So still is the length divided by the width times the height, right? So the width still is delta x, but what is the height? Height is depends on where is this midpoint touch the curves, right? So will be what? X of the x1 bar plus f of the x2 bar, plus f of what? Xn bars here, right? So this is the midpoint rule, and we're going to take a look at the examples, and we're going to, try to do that. Okay, so now, if you understand, then we just basically, it's just a very tedious work when we try to do it without a computer, right? Okay, so now the trapezoid, all right? So the trapezoid is here. From the name, that means we want to use the trapezoid instead of the rectangle to approximate it. So for example, here, this is my f of x. All right, so here the same way, this is my A, and this is my B here. And I'm dividing into several subintervals here, right? So this is x1, x2, and And now you will have this one, right? Okay, so let me try to maybe do one more intervals here. So this is here, this is so this is x3. Okay, so when we try to do the trapezoid, that means for each one here, we will treat it as a trapezoid, right? So the trapezoid, like for the first one, you connect these two, and there will be this trapezoid. Then the second trapezoid will be here, right? You connect here, and then this will be your second trapezoid here. Then the third one's here. Let's see here. So let me see, you find the trapezoid here. Then this will be your third trapezoid here. Okay, so now let's try to see how do we find the area. We know the area of the trapezoid is what? It's base 1 plus base 2 times the height divided by 2, right? So for this red ones here, okay, so for this red one, I'm going to use the red ones here, right? So it will be f of a plus, that's the base ones, right? So here, this is base 1, f of a plus f of x1, right? So the base 1 plus base 2 times the height. So what is the height here? The height is delta x, right? The height is delta x divided by 2. Okay, now let's take a look at the second green one. The second green ones will be the base one. So this will be f of x1 plus f of x2. Then what? Times the height. Height is delta x divided by 2. Let's take a look again. The third one, the golden ones here, this will be the base one. So it's f of x2 plus f of x3 times the height is delta x divided by 2. Then you can continue, depending on how many subinterval you will have, how many, the trapezoid, right? So now if you combine it, so I will know the AB, the f of x dx can be approximated by trapezoid. I used the Tm. All right, so let's take a look. I take the delta x over 2 out. Okay, so if you take the delta over 2 out, so the first one, this is f of a. Then plus fx1. How many f of x1 here? F of x1, f of x1. So I have 2 f of x1. Right, so how about f of x2? I have fx2, I have fx2. So I have 2 of the f of x2. Then I plus all the way till the 2 of f of x and minus 1, then plus what? 1 f of b. Right, so that is what we call it, the trapezoids here. All right, okay, so now let's see here. Okay, so the Simpson rule. So what is the Simpson rule? Trapezoid by name is you use the trapezoid. Then Simpson rule is said I'm going to approximate my integration by using parabola or quadratic. What's that mean here? Let's take a look. Okay, so let's see here. So if this is my function here, right? So this is my f of x function, and so this is AB. This is AB. Okay, so now let's just try to see. I'm going to break it here, right? So then we can generalize that. Okay, so I just want to show you what I mean here. So the Simpson rule is using what? Is using the parabola. So they're using the parabola try to approximate, the curves here. So what I mean the parabola? Let's see here. So in order to use the Simpson rule, so the first thing is here, the n has to be even. That means the number of the subinterval you divide has to be even. The reason why, here is the reason why, see here, right? So the Simpson rule say, I'm going to use 3 points because I know the 2 points determine the lines, right? So the 3 points are going to determine the curves here. Okay, so the Simpson said, we're going to use this one, the quadratic, we have 3 variables, right? So we need to have 3 points to solve it. So this is the 3 points. That's why I have to use what? I have to use like the 2 intervals, right? So that means I can approximately here, let's see here. So like you can say I want to approximate, okay, by using this quadratic, right? I'm going to use this quadratic for here, and then the next ones here, let's take a look at this ones here. That means for here, for this curve, I need here and here, right? So that means my quadratic are going to go like this, right? Maybe I'm going to use a quadratic to approximate this part of the curve. So it turns out the Simpson, the quadratic or parabola is a very good approximation for the integration if your function is a curve. So in here, let's try to write it here. So the AB and the f of x dx. So basically you kind of solve the, you have like 3 points, so you can solve the, because of quadratic we said is ax squared plus bx plus c, right? So you can solve the variables. Then because quadratic is super easy to take the integrations. And there are a lot of the math involved for the proof. So for here, I'm just going to write it out. What is the area, so approximate by, so will be the delta x to the 3. And I'm going to skip the proof. And then here, this is f of the a, right? So every 3 points, right? So now this will be plus 4 the f of x1 and then 2 of f of x2, then 4 of f of x3, then till 4 of f of xn minus 1 plus fb. Okay, so I'm going to write in here, so the constant, right? So the constant coefficient for here, right? So let's say the coefficient for the Simpson will be 1, 4, 2, 4, 2, and then 4, 1. All right. So let's also other things here, because we are using the 2 subintervals right now. So we know the n has to be even for the Simpson. Okay. So for all the others, the approximation that you can have a odd number of the subinterval, but for the Simpson, it has to be the evens here. Okay, so now let's take a look at this problem here. We said I'm going to integrating the -1 to 5, the 2x to the 3 decimal point with a 6 subinterval. Okay, so first, I know for the 6 subintervals, right? So for the 6 subintervals, so you are doing from the -1 to 5. So right, so this is 1, 2, 3, 4, 5, 6. So your x, the x1 and the a is -1, x1 is 0. All right, so now let's take a look for the left-hand point, right? So first here, your I will start with, so you have 6 intervals, right? So you have 1, 2, 3, 4, 5, 6. Okay, so for the left-hand point, so what is my xi? I'm going to use, oops. Okay, so here, okay, so left endpoint, right? So you want to go through the left ends, right? So here, right? So first one will be what? Will be -1. So left ends here, left ends here, left end, left end, left end, left end, right? So it's -1, 0, 1, 2, 3, 4. Am I right? All right. So now you just plug in whatever you point into your function to the x. So let's put it here. So it will be have 0.5, 1, 2, 4, 8, 6, 16. Okay, so now you add them together, you will get a 31.5. All right, so your left end approach is 31.5. Now let's take a look at the right end approach. Right end approach is still the I is 1, 2, 3, 4, 5, 6, right? So you have 6 interval. And now I'm going to the right ends, right? Right ends here. This is -1, 0, 1, 2, 3, 4, 5. So the right end will be here. 0, 1, 2, 3, 4, 5, right? Okay, so now you can have your x stars here. So this is 0, 1, 2, 3, 4, 5. Then you substitute to your function, the 2x function. So your f of x, so this is the 2x star functions, right? You put that in, and you will have 1, 2, 4, 8, 16, 32. So when you add them together, it's 63. Wow, you see it here? This is we call it a right-hand approach. It's 63. So as you can see, the left and the right hand approach, because it will only have 6 intervals, the difference is huge, right? Okay, now let's take a look at how about I use the midpoint approach here. All right, so let's do the midpoint first, and then we'll do the trapezoid. Okay, so the midpoint, the I is 1, 2, 3, 4, 5, x. Then the xi here, the f of xi star. Okay, so the midpoint here, so this is 0, 1, 2, 3, 4, 5, negative 1s, right? So the midpoint will be what? Here, right? Here, 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 here. Okay, so let's try to write down the midpoint. So what is the first one here? It's a negative 0.5. Then this is a positive 0.5. Then it's 1.5, 2.5, 3.5, and the 4.5, right? All right, so for all this midpoint, now you plug it into a function 2 to the x star. So this is 2 to the x star. All right, so you plug that in, so you will get this 0.707, 1.414, 2.828, 5.657, and this is 11.314, and you have 22.627, and when you add them together, you will get 44.547, right? Okay, so this is what we call it, the midpoint approach is 44.547. Okay, let's take a look at the trapezoid. All right, so trapezoid here. So the same way here, my eyes is 1, 2, 3, 4, 5, 6, right? Okay, so now my xi here. Okay, so this is my f of xi. Okay, so xi is just negative 1, 0, 1, 2, 3. 0, negative 1, 0, 1, 2, 3. Oh, I'm missing here. So this is 0. Okay, so with the trapezoid, we need to be careful here. All right, so let's start over again. All right, so I'm going to have a 0, 1, 2, 3, 4, 5, 6. So the first one will be negative 1, 0, 1, 2, 3, 4, 5. All right, so because take a look here, right? So this will be my negative 1, 0, 1, 2, 3, 4, 5, right? So first I need to use this one, add this one, right? So f of negative 1, I will get it, then you put it into the function. This is 0.5. So this is 1, 2, 4, 8, 16, 32. But remember, right? So the way you add, right? So this term here is f of a, so it's 0.5. Then you have 2 of it because you have 2 trapezoid here, right? So you have 1 trapezoid here, then you probably have another trapezoid here. So f of 0, you add 2, right? So it's 2 times 1 equal to 2. Then you have 2 times 2. So here is 4. Then you have 2 times 4. Here is what? Is 8. Then you have 2 times 8. And you have 16. Then you have 2 times 16. You have 32. Then you have this 32 just by itself. See here. Then when you add them together, you will add those numbers, right? Okay, so you will add those number. Okay, so this will be 94 point what? 94.5. So now I plug into the trapezoid. So trapezoid 6, remember, is delta x what? So it's delta x over 2, right? Delta x is 1, so it's over 2, 94.5. So what is the answer? This will be 47 point what? 25. Okay, right? Okay, so now let's take a look at the Simpsons here. Okay, so this one here is the one we're not familiar with, right? Okay, so now let's do the same way here. So because I'm going to use the first one, so I'm starting here, 0, 1, 2, 3, 4, 5, 6, right? 6 intervals. So the xi here is the same thing, start with -1, 0, 1, 2, 3, 4, 5. Then we put the f of xi. So this is a 0.5. Then we have 1, 2, 4, 8, 16, 32, right? Okay, now here is the terms, right? Term is a pointer, so FA is a 0.5. So what is 1, 4, 2, 4 twos, right? So this one is 4 times 1. So it's 4. 1, 4, 2. So it's 2 times 2 is 4. And 1, 4, 2. So it's repeat 4 again. So it's 4 times what? 4 times 4 is 16. Then 2 times 8 is 16. 1, 4, 2, 4, 2. So the last one is 4. 4 times 16 is what? 64. Then the last one is self. Okay, now let's add it. So those are the number I need to add it, right? So when I add it, my sum will be what? 136 point. So 136.5, right? Then we know the Simpson will be delta x over 3. So delta x is over 3, right? And times the sum, 136.5. So it's 1/3 times 136.5. So what is the Simpson will give us? Will give us 45.5. Okay, so now let's take a look. This is really cool. Since we already know how to do the integration algebraically, we have the formulas, right? So I can do that. So it's -1 to 5, the 2 to the x, the dx, right? So we know, okay, so for this ones here, we can, find the integrations, and we know the exponential function, the integrations, and then this one will turns out to be equal to the 63. So if you really carry out the integrations here, it will be, okay, so we can use our basic integration. So we know this one, this one will be, I think it's a natural log 2 and the 2 to the x and the -1 to 5. And if you substitute back, so this will be natural log 2. 2 to the 5th is 32, and the -2 to -1 is 1/2. If you simplify it a little bit, this will be 63 to the natural log 2, right? Or you can say this is a 63 natural log 4. So if you plug the number, and it will be pretty close to the 45.445. Plug the natural log 4 into the calculator. So this is 45.445. That's the true integration value. As you can see, the Simpson really work out pretty good, right? So it's 45 here, right? So 45, and then trapezoid is kind of close, it's 44. Then midpoint, So the our midpoint is 44, and the trapezoid is 47, and then like you see the left endpoint, the right endpoint is kind of off a lot. All right. Okay. So this is the video number 1 we're going to talk about is to try to how to find the approximation of the definite integration by using 6 different methods here. All right. And it's, as you can see, the each one is pretty unique, right? The trapezoid, the midpoint, the Simpsons, and the left point and right points. All right, that's it. And then in our next video, we're going to talk about when we use different approximation methods, how much errors we're going to have. So for example, for here, right? So the real integration is 45.445, and my Simpson is 45.5. So what is the error of the estimation? What is the maximum error I'm going to have by using each different methods here? That's what is the next video we're going to talk about it. All right, so nice to talk to you, and you have a good day. All right, bye-bye.